Imagine the simplest possible setup in electrostatics. Two charged particles, suspended in empty space, sitting a few inches apart. Thanks to a formula known as Coulomb's law, we can calculate the exact force between these two charges. If we know their distance and how much charge they carry, the math tells us precisely how hard they push or pull on each other. But if you open a physics textbook, you'll find a strange intermediate step inserted into this interaction. Instead of calculating the direct force from particle A to particle B, the book introduces a middleman called the electric field. In this static view, the field is often treated as a convenient calculation tool, a layer of bookkeeping used to find the final force. To see why the field matters, we need to change how we look at that empty space. Imagine we have one stationary charge, a source charge. Now we bring in a tiny, positively charged object called a test charge and place it nearby. The test charge immediately feels a force. If we move it to a different spot, it feels a different force. The electric field is simply a map of this electrical environment that the source charge has built around itself. Notice that this environment belongs entirely to the source charge. The field exists at every point in space, completely independent of whatever tiny test charge we decide to drop in and measure it with. Mapping the environment this way shifts the focus to the properties of the space itself. It is a change in perspective that sets the stage for a much bigger realization. Let's remove the test charge entirely. What happens to that space when we have a whole system of stationary charges arranged together? These multiple charges combine to create a continuous vector field, assigning a specific direction to every coordinate in space. It also gives the exact magnitude of force. Close to the charges, arrows are long and dense. Farther away, they weaken. As a topological map, this grid is a highly elegant way to visualize a static configuration. But as long as the charges sit perfectly still, we could technically survive by just using Coulomb's direct force math. The true physical necessity of the field only emerges when things start to move. Let's introduce a complication: time. Suppose we have two charges sitting far apart from each other. Now we violently accelerate the first charge. Does the second charge instantly feel the change in force? Does it somehow immediately know that the first charge has moved? Here we run into a major physics problem. The universe has a strict speed limit, c, the speed of light. Absolutely no signal or information can travel faster than c. Because of this rule, there has to be a finite time delay between the moment the first charge moves and the moment the second charge reacts. Instantaneous action at a distance is impossible. If the physical force doesn't teleport instantly, something has to physically cross the empty void to carry the message. The time delay identifies the electric field as a physical entity, a messenger bridging the void. When that first charge accelerates, its motion produces electromagnetic waves. These waves ripple outward at the speed of light. The ripple propagates through space, carrying energy across the void, until it reaches the second charge and pushes it. Because the field elegantly accounts for this time delay, it proves it has its own substance. It is a mechanical gear of the universe, doing real physical work. We can take a source, turn it on for a moment, and then switch it off. The fields it generated will continue to evolve and propagate outward, transporting energy completely independently of the particle that created them. Michael Faraday imagined the space between objects as a medium of lines of force, a fabric that actively participated in the electrical interaction. Modern physics confirms Faraday was right. Electric and magnetic fields are physical entities. They have their own independent dynamics and evolve according to their own laws. Mastering the concept of an electric field is about learning the true mechanics of interaction. It is the physical fabric that allows everything in our universe to touch everything else.